So I already have discussed a few of amplifier based circuits, important circuits, and one of them was unity gain, which I have discussed in previous slides as well. So I also have said why we use unity gain amplifiers, because you need to convert the you need to use this as a buffer to a particular circuit so that the resistance doesn't mismatch. Okay, so just here also I have given you an example like previous case. So what I did is I put this 100 kilo ohm resistor in series towards the input side. This is your Vin, right? And if you put this 100 kilo ohm resistance in the input side, what is the condition for this OPAMP to work as a nice unity gain circuit? The condition should be your Ri, that is whatever is appearing here, should be much greater than 100k. I also said previously that you just cannot increase in case of feedback. When there was a feedback, I said that you just cannot increase your R2 value, or when there was a feedback, right? You just cannot increase your R2 value the way you want. It is not recommended, because if the external resistances becomes close to the Ri, then you will find that it is influencing the OPAMP circuit, and in that case the assumption that the current going inside the OPAMP is equal to 0 may not valid. So the only condition that you have to satisfy is, in such a case, your input resistance in this side should be much higher than the 100k. If this is okay, then you can even put 1k load resistance. It will not be a problem, right? So you can use then a very low resistance, almost 100, right? Almost 100 times less resistance, load resistance, and it will not be a problem in the circuit. So this was the reason why we use buffer, and unity gain amplifiers can be used as a buffer. And another thing I said, it will also help you to drive less current. Otherwise, for a very low resistance, it will drive a lot of current from your source, which is not recommended. Your power dissipation will be way higher. Then there is another circuit called IV converter. IV converter means your output voltage will be a linear function of your input current. Okay, so your output voltage would be a linear function of input current. So in this case, if you use this type of circuit, if this is your requirement, if you use this type of circuit, here it is very evident that your I1 is equal to I2. This current and this current both are equal, because this place is it's a virtually ground, and there is no current going inside. So your I1 will be equal to I2, which is equal to Is value. Okay, now if you see your I2 current, which also can be written as 0 minus V0 divided by Rf. So 0 minus V0 divided by Rf is equal to your I2. So from here you will get the relation of V0 is equal to minus I2 Rf. I2 and Is are same, so V0 is equal to minus Is Rf. Here it is written. So your output voltage becomes a function of input current. So your input current will decide now what will be your output voltage. So it's kind of a current controlled voltage source, right? Current is controlling your output voltage. So this type of circuits also is possible using OPAMP, and in many cases in real-time application you will find these circuits are used. Okay, just to give you some idea about different OPAMP application, I am showing these circuits. These are also available in books, you can study, but it is important to know this type of circuits, because later on it will be useful when you are doing actual design and etc. These circuits will be useful. At least it will be in your mind that we can make this type of things using OPAMP. So whatever we are studying is not just for the sake of study. There are applications. You can make different circuits as well using this op-amps. Now there is an interesting circuit which is VI converter. Now most of the op-amps are VI converters, so it's not something new, but the speciality of this circuit is your output current will not be a function of load. So whatever is current flowing through the output, I mean whatever you current get in the output, it's not a function of the load. That means you can use any load, but the current will be same. This is my requirement. So in such a case, we have rearranged the circuit a little bit, and let's see after analysis what it comes. So even in this circuit, if you see, your I1 will be equal to I2. These conditions are almost valid everywhere, and we are making sure that these conditions are valid. As I said, your Ri should be very, very high, then it will make sure that no current is going inside, and this potential is equal to this potential. Okay, otherwise this assumption will be invalid. So one has to remember that there are some conditions to make these statements correct. In fact, I'm mentioning almost everywhere. So your I1 is equal to I2, and your V minus will be equal to V plus, which is equal to VL. The potential over here is taken as VL. It is not ground. So remember, in this case, it is not grounded. It is grounded through this resistance. So whatever is drop across this resistance is appearing here, or whatever is drop across this load ZL is appearing here, and these two nodes are shorted. So this particular potential of this node is VL. So in this case, your V minus will be equal to V plus will be equal to VL, which is not equal to 0, right? And your I1 is equal to I2, as no current is flowing inside. So whatever is coming here will directly go through I2. Okay. Now, if you look at the current I1, it is nothing but V in minus VL divided by R1. This is your I1, V in minus VL divided by R1, and your I2 is, if you see, your I2 is VL minus V output divided by R2. This is VL, and this place is V output. So VL minus V output. So VL minus V output divided by R2 is your I2, and we know these two are equal. So V in minus VL divided by R1 is equal to VL minus V0 divided by R2. What is VL? This potential, we can write VL is equal to IL ZL, right? So VL is equal to IL ZL. Just put this value IL ZL in the place of VL. And what is the value of I3? I3 will be, if you see, it's V0 minus VL divided by R3. So V0 minus VL divided by R3, and just put the value of VL, it is IL ZL. So you have the value of I3 as equal to, I3 is equal to this. Now put KCL in this node. Your I3 is equal to IL plus I4, right? So your I3 is equal to IL plus I4. Is that okay? Because this current through this is very less. I already have said no currents is flowing inside the op-amp. So all the current that is coming will go through R4 and will ground. R4 to ground. Okay. So this is I3 is equal to IL plus I4. Now put the values. I3 is equal to V0 minus IL ZL by R3. This is IL, and I4 is, this I4 is VL by R4. Now VL is IL ZL by R4. So it is also written here. Okay. So if you do this, you'll find equation 3. Now if you replace this value ILZL, V0 minus ILZL, here also you have ILZL minus V0, which is equal to minus V0 minus ILZL, right? Just take the minus common, so it will be V0 minus ILZL. So if you replace this value in equation 1, or if you calculate the value of this and replace it in equation 3, so from 1 and 3 you will get, if you do the calculation, you will get something like this. So your IL will become this expression. Now your purpose of this calculation is to make IL independent of ZL. So if you want ZL to disappear, this term and this term should cancel out. So this minus this will be 0. You want this minus this term should be 0. In such a case, here it is 1 by R4, this, right? And here it is R2 divided by R1 into R3. So I repeat, this one it is R2 divided by R1 into R3, and here it is 1 by R4. So these two terms should be equal, then these two will cancel out. So if R2 divided by R1 plus R1 R3 is equal to 1 by R4, you can write that your IL is equal to minus, because it is minus 1, remember, so it will be minus 1 by R4, because this part is also 1 by R4, right? So it will be minus 1 by R4 into V in. So you find that your IL is independent of ZL. So whatever value of ZL you put, your IL won't change. So it's kind of a constant current source. In many places people use this circuit as a constant current source, provided you have to maintain this condition. That's it. Okay, so if you maintain this condition, you will find that your IL is independent of ZL, that means the load. Okay, so similarly we have other interesting circuits like differentiator and integrator. Now these circuits are important also in filters. I'll tell you why these are important in filters. Just after this we will start filters. Okay, so in filter circuits you will find these circuits are important. So it is also important for you to know these circuits now. Now what is a differentiator and integrator? This is also a circuit, but if you see the operation differentiation and integration, they are just opposite to each other, right? Differentiation and integration is just an opposite to each other. So if you have a differentiator circuit and just make it opposite, you should get an integrator circuit, right? So this also happens in this case. Now if you look at this circuit, this is a typical differentiator circuit where you have a capacitance in series and you also have a feedback resistance. So the current through the capacitance in this case will be C dV in dt. This is the current entering. So if you have a capacitance in series, what does that mean? That means it will only allow AC to flow, no DC current, right? So this is for AC analysis. So what is the current through R2? It will be the same current flowing because no current is entering the OPAMP. This condition is still valid. So current through R will be, this place is 0, virtual 0. So it is 0 minus V0 divided by R is the current, which is equal to C dV in dt, right? So if you rearrange this equation, R will go this side, so it will become RC, and minus sign is there. So if you multiply minus on every side, so it will be minus RC dV in dt is equal to V0. This is what it is written. Okay, so V0t is minus RC dV in dt. Now let us consider the impedance associated with the capacitor, which is 1 by Cs. Now in this case you can write V in minus 0 divided by this impedance 1 by Cs is equal to 0 minus V out. This is V out. This place is V out. So 0 minus V out divided by R. Both the currents are equal. So from this equation you will get V0 is equal to minus RCS V in. That means V0S divided by V in S is minus RCS, or S is j omega, S equal to j omega. So it will be minus j omega RC. So you have a transfer function now which is RC into S. Here RC is the time constant and your phi value, phase value is from, if you have A plus JB, then tan inverse is B by A. Just apply this rule, you will find your phi value is minus pi by 2. Okay. So you have a differentiator circuit where if you plot the Bode plot, you will find that you have a 0, and this 0 will be shown something like this, a straight line with 20 dB per decade, that we already have discussed previously, right? If you have a 0, it goes upward at a rate of 20 dB per decade. Okay, now for some reason, if you can make this part flat like this, and this is your frequency, so what does that mean? It means that in low frequency there is no gain, nothing, and at high frequency this circuit is allowing the signal to pass. So that means it's a high pass filter. High frequency can pass, so it's a high pass filter. Similarly, just now, what do you expect for integrator? This is differentiator which acts as a high pass filter. So in integrator, what do you expect? Because it's just opposite, you will find a low pass filter. And then if you arrange this differentiator and integrator together, or if you use them together and arrange these values, you will also get a band pass filter or a band reject filter. So filter is nothing but a concept that came from this circuits or this type of Bode plots, you can say transfer functions. Okay, so similarly, I am not going in details of integrator. So in case of integrator, you have just put resistance in the place of capacitance and capacitance in the place of resistors. Capacitors in the place of resistor and resistor in the place of capacitor. So you get this circuit which is integrator. Similarly, your V in by R is your I, because this is 0. So V in minus 0 by R is equal to I. And what will be the current through this? It will be minus C. Now this is dV0. So it will be minus C dV0 dt. So you will get some expression like this, where VCO is the integration constant. What does that mean physically? That means if your capacitor is not completely discharged, you will find some voltage across this VCO. So to make VCO, to make this term equal to 0, you have to make sure your capacitor is completely discharged. For example, say you are using this integrator for a long time, and then when for the next cycle you are planning to use, you did not discharge your capacitor, then you will find this constant. So you have to make sure your capacitor is completely discharged, and for that purpose, mostly what people do is they connect a parallel resistive circuit, switched circuit. Switched circuit means when they are in operation, this will not come into the picture. Just at the end of operation, it will help the capacitor to discharge completely. So you need a discharging path for this capacitor, otherwise this term will appear everywhere physically. So you will get again a transfer function which is similar to minus 1 SCR. So you have a pole this time. So pole means it's 20 dB per decade downwards. So if you get something of this sort, then this is a low pass filter. So you have to be very I mean, if you combine both integrator and differentiator, you can make different kind of filters. So we will use this type of circuits in the next topic when we will start filter, and then we will explain in detail. So you have to be very much careful about where you want your cutoff frequency to be, because this is very important in case of filters.